All right, so for my lab, we did resistive forces. I am Julia Eckberger.
I'm Dalton LeBar.
I'm Olivia Jenny.
All right, so our goal for this research project was to determine the velocity of the three different liquids using the terminal velocity of dropping a ball. By observing the point at which the ball achieves a steady speed or terminal velocity, we can apply those principles of fluid dynamics to calculate the viscosity. So our research question was, how can the terminal velocity of a falling spherical object be used to accurately determine the velocity of the three different liquids? All right, so for prior knowledge, we use the viscous fluid force equation, which is we use it as a solid object, the marble moving through a fluid as the drag of the fluid on the object that you dropped. Um, Therefore, the equation is down below. All right. So for our experimental design, what we did is we had to figure out an independent variable, which we knew was height. We did a dependent variable, which was the terminal velocity and the viscosity that we will calculate. And then we kept the constants the same. So the same ball, so it has the same shape, the same mass, and they're all dropped from the exact same measurement for height.
So our sources of error were velocity, height measurement, and environment. So we can't control the initial velocity because we needed it to drop through the air before getting to the liquid. And then it's just human error for the initial height because we can't have it be perfect. And then our experiment was not done in a closed environment, so like the free fall will be assumed. And then for reduction of error, we had a designated person from the group to drop the ball, and so this increased the likeliness that a similar force will be applied when the ball is released. And then we had a meter stick for the height measurement in the video to ensure accurate height, and then the ball was cleaned between each trial so there wasn't residual liquid. And then are our visual representations, like our system schema, our energy pie charts, and our motion maps. So for each trial, we dropped a ball. This one's glycerin. So we dropped it from 60 centimeters into the graduated cylinder, and then we tracked the ball's velocity as it went through the glycerin using tracker software. Our initial impression was that we observed that the ball's velocity changed once it hit the glycerin. This might be due to the viscosity of the glycerin showing the marble down as it pushes through the liquid. And then we just repeated that for dish soap and syrup.
Okay, so these were our results. Um, we wanted to calculate it when it reached terminal velocity, which means that the acceleration was zero. Um, so we looked at the acceleration graph and we saw that point in time when it was zero. So that means on the position graph, you'd see it as a linear segment. So we took that linear segment and we created a trend line for it to give us an average velocity of the terminal velocity. So for trial one, we found that to be negative 1.507. And then using the equation that we came up with earlier, we calculated the viscosity to be 1.93. And then the same thing happened for dish soap and syrup, giving us negative 1.19, 2.45, negative 0.1135, and 25.65 respectively. And then in conclusion, we found that using the position graph, in addition to the other graphs, we were able to calculate the viscosity of three different liquids using their respective terminal velocities. So to find their terminal velocity, again, we found the slope of the position graph when acceleration was zero or when the graph was linear. And then we found their viscosities to be in ranking order: the strongest syrup, the next strongest dish soap, and then the weakest to be glycerin.